Okay guys, so we've got the ideal gas law up next, and what I want to do is I just want to touch base on a couple of concepts we've already covered before and see if we can't just sort of make this formula, derive this formula up from information that we've already learned. So first thing that I want to point out are these two standard conditions, if you remember STP and SATP. These are found in your data booklet, and I've written them up here on the board as well, but these numbers here we haven't really touched on very much. And these are what are called molar volumes. So if you remember, we talked about molar mass, which is grams per mole. Molar volumes is liters per mole. And if you remember from our previous lesson about the law of combining volumes, what we learned in that video was that every gas, doesn't matter what it is, if you have 1 mole of that gas, it is going to occupy a certain volume, volume X. Well, if I've got a gas at this pressure and this temperature, that gas is going to occupy 22.4 liters of space if you have 1 mole of it. And that's for every gas. And if I change the conditions up a little bit to be SATP at this pressure and that temperature, the gas is going to occupy 24.8 liters if I have 1 mole of it. So if I have 2 moles of that gas, I'm going to occupy a larger volume, obviously, a volume twice as big. Now, what we do know about these different conditions in terms of Boyle's law, Charles' law, and the combined gas law is that we know that pressure is inversely proportional, and this little symbol here just means proportional. And it's inversely proportional to volume, so that's why I write volume as 1 over V. So it just means that as the pressure goes up, the volume is going to go down. And for a gas, also we know that the pressure is directly proportional to 2 other concepts. So the first one we've learned about is just temperature. Temperature is directly proportional to pressure, and that's from the combined gas law. As well as, though, a new concept here, which is just N, which is the moles of a gas. The more moles of a gas that I have in a confined space, obviously the more pressure I'm going to have. So if I were to have like a scuba tank or whatever that's got my oxygen in it, if I put more molecules of oxygen inside that scuba tank, then the pressure is going to be higher. And so this makes sense. Pressure is directly proportional to the amount of the gas, moles. Now, if I just substitute this proportional symbol in for an equals sign, which we can do often, we get P is equal to NT divided by V. And if I rearrange that algebraically so that everything is on the same side of the formula, I'm dividing by V over here, so I got to multiply by V to get it over to this side. And so I get PV, and then this is multiplying by N and T, so I divide it to get it on the bottom over here. PV divided by NT is equal to some number. So what I want you to do is I want you to pause the video and plug the conditions of STP into this formula and see what number you can get out over here. And I'll be right back with the answer. Okay, so we're back with our little problem that I gave you. Hopefully you're able to plug the numbers in. If you weren't, that's okay. Just follow along and we'll sort things out for you. So we've got our STP numbers plugged into this formula. So pressure at STP is 101.325. The volume at STP for any gas is 22.4 liters. And that's for 1 mole of that gas, right? So 22.4 liters per mole. And so you can see I stuck the mole unit down there in for N. And then the temperature is 273 Kelvin. I plug this into my calculator and I should get a number that is 8.314, and here's the units: kilopascals times liters divided by moles times Kelvin. And that looks like a mouthful. It is. It's not something you need to memorize. That's in your data booklet in the place where you're given a bunch of other numbers and STP and SATP and all that kind of stuff. And this is called the ideal gas law constant, and it's denoted by the letter R. And so really what this is here is that little question mark is R. And we can rearrange this formula so that we don't have any fractions, that we've just got everything on the top, because we like to do formulas that are like that. They're easier to manipulate. And so N and T will cancel out, and N and T go there. And if I kind of just rearrange things a little bit more, what you'll notice in your formula sheet is we've written this formula as PV equals nRT. And so this is the ideal gas law right here, this formula. And so in the next clip, I'm going to do a couple of examples for you guys to just show you how this formula works and get you on your way. So here's our example that we're going to go through together. You can see I've got the formula written up here at the top. And one thing I want to point out before we look at the work for this problem is take a look at the R value. The R value is 8.314, and the units are kilopascals times liters per moles times Kelvin. Now this is important because if you remember from the previous lessons with Boyle's law and Charles' law and the combined gas law, is that it's okay to use whatever units you want to use as long as the units are consistent. And so for those formulas, if you had milliliters here, then it punched out as milliliters. But because R has a set amount of units, we still have to make sure that we are using those units consistently throughout the formula. So because R has units of kilopascals, then our pressure must be in kilopascals. So if you're given a problem where they give you a pressure, but the pressure is in atmospheres, you can't just plug that number in atmospheres into this formula and expect to get the right answer, because you won't get it. And it's because the units are not consistent if you use atmospheres. So make sure that your pressure unit is in kilopascals. Your volume unit, because R has units of liters, then has to be in liters. And moles must be in moles, not kilomoles, not millimoles, has to be in just moles. And obviously temperature has to be in Kelvin as well. So when you plug these numbers in, if you take a look at this problem here, for example, it says, you know, predict the amount of moles of methane that you've got given these conditions. So the conditions are that you've got 475 milliliters. So first off, that should ring alarm bells in your head saying, hey, that's not in liters. This is the ideal gas law. I have to use units of liters for this number. And so what I like to do is I like to write my numbers down as I need to plug them into the formula so that I can make sure I'm double checking all of my units. And if you can take a look here, I've made a mistake here with my volume where I've converted it into liters but then wrote it as milliliters just by mistake. And so this should be 0.475 liters for that. And so 205 kilopascals, that matches. Liters, that matches. 0.475 liters is equal to 475 milliliters. My temperature is converted into Kelvin, so 31 degrees Celsius converted into Kelvin. Moles, I don't know what it is, and my R value right there. And now I can just go ahead and plug this in. So you can see I've rearranged my formula here to solve for N. And I did that by isolating N by dividing by RT here so that the RTs cancel. And what I do to this side, I must do to this side as well. So PV divided by RT over here. So N is equal to PV divided by RT. A common mistake that kids will make is they will try to do this rearrangement in their head. And I see many, many times, this is one of the most common mistakes I see in all of Chemistry 20 course, is that when kids go to write this formula, they will write it as N is equal to RT divided by PV. And that's the reciprocal of the right answer that you're going to get, or that's the reciprocal of what would be the right answer. And so this is going to give you obviously the wrong answer because it's not the correct formula. My high recommendation is when you are manipulating the formula, do it on the page so that you can see the work and making sure that you're manipulating it correctly. And so that is not right. Don't do that. So N is equal to PV divided by RT. Plug my numbers in, you plug it into your calculator, and you end up with 0.0385 moles. And if you take a look at the units here, they all cancel out. Again, I've made another mistake here with the milliliters. This should be 0.475 liters. And this is the main reason why I want you guys to write your units into the formulas, so that you can double check to make sure, hey, I'm doing the units right. Lots of times kids might go here and they'll go 475 milliliters, and if they write the milliliters in and then they physically go in and cancel the units out, they go, oh shoot, I wrote in milliliters, I need to change that. And it's a safety net so that you can double check your work while you're doing it to make sure you're doing things right. So if you see, I've got kilopascals on the top and the bottom, I've got liters on the top and the bottom, and I've got Kelvin here on the top of the bottom, and Kelvin on the bottom of the bottom. So that cancels that as well. And I'm left with units of moles, which is exactly what I want my answer to be in. And so hopefully this helps, and you guys are free to start working on your practice questions. Good luck.